Welcome to the 28th class meeting of EECE341, Introduction to Communication Systems. Today is the last class meeting, and of course, according to our rule book, there will be two more class meetings, but they will be all converted to have you all present because we have our midterm and final exams not in our regular class meetings. So including these 2 days, we meet the 30 class meetings. So if you find something wrong with the rule book, please tell me and provide evidence so that I can correct it before the final grade is given to you. As usual, homework is again assigned and will be assigned. And we have the final exam on Friday, 20th, from 7 to 10 p.m. here. And it's an open everything exam. So, and also you must be able to upload your solutions to the PLMS. So please be well prepared. For the voluntary project, you have to decide whether to do it or not before you take the final exam. And it's due on Thursday, midnight, December 26th. Here goes the messages from my instructor, and now you know what does this Petronas Twin Towers mean. There was no anything to correct or clarify. And in the last class meeting, I talked about FSK and QAM, OFDM, and some other modulation schemes, which will be covered in detail in the digital communications course offered in the next semester. Today's topic is information theory, and we are going to cover it. So this is the slide for the first handout. And in the first week, we stopped just before this page is given. So we are now have come back to this page. So most of you are electrical engineers, and electrical engineers are, interestingly, must handle uncertainties. These days, the situation a little bit have changed, but around 10 years ago or 20 years ago, interestingly, most of the quants who are the designers of some algorithms in our Korean Wall Street called Yeouido stock industry, many quants were electrical engineering background. Why? Because there were not many undergraduate majors who taught probability and statistics thoroughly and seriously. And even when I was an undergraduate student 30 years ago, and there was a mandatory course, probability and random processes. So at that time, almost all electrical engineers were taught how to handle uncertainty using probability theory. That is quite interesting because Claude Shannon, we will see his picture again here, was also an electrical engineer. So this guy, okay. As his career says, he was an undergraduate student in the electrical engineering of the University of Michigan. And interestingly, he interested in mathematics, so he minored mathematics with emphasis on probability and statistics. Then, after getting the bachelor's degree, he moved to MIT and continued his study in communications. And he was one of the first engineers, electrical engineers, who seriously combined probability theory with communication theory. Even before him, there were engineers who combined the probability theory with communications, but he was really serious in doing that. So you see the kind of trend. From long ago, in the beginning of information communication theory, electrical engineers had to handle uncertainties. In the first handout, I have shown you the Babel Tower in the biblical structure, which has the story that the God got angry and make the language of the workers different. And due to the lack of communication, it collapsed, something like that. And why we do communications? Because of the imbalance in information between two parties in communication. So there is uncertainty from the beginning in communications. Otherwise, we don't need to communicate. We all know everything, right? And one of the way to mathematically handle uncertainty is to use probability theory. That is why probability theory has been with electrical engineers for a long time. And that trend allowed the opportunities for the electrical engineers to become, for example, Wall Street quants or Yeouido stock market quants. Now, more and more mathematicians have interest in handling uncertainties, especially for financial signal processing. So the rumor says that our national pension system, now the main headquarters located in Naju or Jeonju, I'm not so sure, but recently hired graduates of prestigious universities mathematics department. So they can better handle our national pension so that the Korean people can rely on the pension after the retirement, something like that. So it is no exaggeration that you have to study and you must be very well equipped with the tools learned in probability and statistics. Interestingly, before Shannon, the communication theory was not that seriously, how to say it, fundamentally mathematical. But he really built up some mathematical theory of communications to handle the uncertainty. So let's see. Around 1948, you know what was going on at that time in Korea. And he published a paper called A Mathematical Theory of Communication. And that changed everything. And he believed, and he is regarded to be the father of information age. And today, we are going to learn what kind of problems he mathematically formulated and derived some very mathematical results. Before talking about information theory, we cannot avoid talking about statistical inference. And what is statistical inference? What is non-statistical inference? We know about so-called logic. And what is a logic? Logic is all related with not, and, or combination of these things, right? And you know, interestingly, we electrical engineers seriously handle this logic using logic circuits. So you have been taught throughout the curriculum of electrical engineering the most important things in human life. And interestingly, logic is generalized to what? Probability theory. And many of you may say that, what? Logic and probability theory is so closely related? Actually, yes, it is. And you remember from our Mathematics for Electrical Engineers A, 전자수학 A, that the first few chapters of probability and random processes textbook talks about complementation of a set, intersection of two sets, and union of two sets, and others. Now, do you see something similar? Actually, this not is related to the complementation, and is related to the intersection, and or is related to the union of two sets. And if you have the probability of event, for example, A, is either 1 or 0, then you know the probability of event A complement is 0. Actually, this is the case when your probability theory reduces to the common logic. But if the event of A is not 1, but for example, 0.3, in that case, you now have something not exactly true or false. It's in between true and false, but you can quantitatively handle the uncertainty now. So I hope many of you now get this claim in mind. Logic is a simplified probability theory. And probability theory is a generalization of logic. Got it? Now, why inference is related to the probability theory? What you do with logic is actually inference. So the famous inference is this. A implies B and B implies C. Then the question is, A implies C. And you say, yes, this is logic. And you may say that, oh, is it related to not and or? And actually, I'm not sure, but many of you have learned this in your high school math. During the last 30 years, the high school mathematics curriculum has significantly changed, and it was actually diluted to include many middle school mathematics of my age. But when I entered the high school, the first chapter was about the logic and the set. Okay, set theory with logic, actually. So the first topic was like if A implies B, B implies C, something like that. And we had a lot of truth tables in the first chapters. Now, this is kind of non-statistical inference, right? There is no uncertainty. Something is true or false. Now, what about here? This is all related with statistical inference. So what you do is like this. For example, probability of event A is 0.3. Probability of event A given the occurrence of event B is also 0.3. What does this fact says to us? And we coined the terminology of statistical independence between two events. And in this case, this conditioning on the event of the occurrence of the event B does not affect the probability of A. So this is kind of posterior probability, and this may be interpreted as prior probability of both event A before and after the occurrence of event B. Since the probability does not change, we say what? The event A and B are independent. And sometimes we use this double perp notation. So event A is independent of event B. Then what can we say? Actually, this gives us a lot of ideas. For example, in this big data time, you have too many information. For example, suppose you are an engineer, financial signal processing engineer in some company. In a fraction of seconds, for example, the Kospi has more than 800, probably Kospi and Kosdaq, more than 1,000 companies. Prices changing. Even though you restrict to 200 stocks, you have time varying 200 random processes. You have to process that, but you want to reduce the number of observations. And what can you do? For example, you find some stock price, a stock price is very, very unrelated to the price change of stock B. Then, and if you are focusing on the price of stock A, then you want to just ignore that information. Then you can kind of compress the information a lot, just finding the independence. Or sometimes a weak version of independence like uncorrelatedness. And also sometimes what you want to do is like this. We want to find out the expected value of some quantity. Before observing some event, this is 0.3 and variance is 1, for example. But if you observe some event, by the way, this is random variable and this is event. After the observation of event A, you have conditional expectation, the same, but variance is a lot reduced. You observe something like this. What can you say? So you may logically say that now this value x is very likely to be around 0.3 with very small error because variance is very, very small, right? So by using this statistics or probability theory, you can say more than before. Now in communications, suppose here is your source. And source generates some message, let's say message M. And here is your encoder. And here is your channel. And here is your decoder and sync. The decoder wants to estimate or guess what was the message originally sent by the source. And you have channel that possibly introduces uncertainties. So this channel is not a mapping rule, simple mapping rule. It introduces uncertainty. Of course, some channel, some deterministic mapping rule also introduces uncertainty. Let me give you an example. Suppose your input-output relation is simply this. So the output of your channel is the absolute value of the input. Now the sign is gone. Then you receive 5 here. Then suddenly you have uncertainty on X, right? So it may be difficult to guess what was M, For example, if you use some bipolar line code or something like that, right? Because the sign is gone. But sometimes channel really introduces uncertainty, something like that. So here goes your channel input, and your channel output is mathematically well modeled as the channel input plus some noise or interference that is probabilistically modeled. For example, N is Gaussian with some zero mean and variance sigma squared. And this actually occurs in communication system. For example, consider radio communication. Here is your transmit antenna. And your receive antenna is located around 20 kilometers away in the Homigot, the Cape Homi. Now, you apply some transmit signal to the antenna with around 1 watt power. Now, in the receiver located at Homi Cape Homi, it receives the signal, and what do you guess? The received signal power is around 100 dB attenuated. What does that mean? The power is, the received power is the transmitted power times 10 to the negative 10. It's very, very small. Now, what do we do in the receiver? Of course, we have some pre-select filtering, but we amplify the signal a lot. If we amplify, use low noise amplifier, even though the name says we do not want to add much noise, we even can see the jitters of electrons in our conductors, like antenna itself. This is a metallic conductor. And you have cables. And inside, we have electrons that carry the voltage or current flowing in the antenna and circuit. And since due to the thermal noise, because we are living in higher temperatures than 0 Kelvin, everything jitters, even electrons jitters. And even though it's a free electron flowing in the metal, free does not mean it is not affected by the grid of atoms. So when it moves from one atom's orbit and another atom's orbit, what happens? There is some resistance. And sometimes this electron goes backwards and forwards, even though there is no voltage applied. That is called thermal noise. And this thermal noise, in our ordinary circuit laboratory, you cannot see. However, in RF communications, with very weak desired signal, with very high amplifier gain, you really observe noise. For example, if you use spectrum analyzer, without applying any signal, you can see the noise flow in the scope. That is due to the thermal noise in your circuit. Since the received desired signal is so weak in long distance communication, not in Wi-Fi, okay, we amplify the signal a lot, and this thermal jittering is also amplified, and we can observe. And one of the way to model that kind of thermal noise is to model the noise as an additive Gaussian noise. Of course, in some cases, this modeling the noise as additive Gaussian noise is very dangerous. However, we start from the simple model. And the simplest is to model the noise as Gaussian noise. So if you take the digital communications course, probably Professor John Joseph, when he first introduces the communication channel, probably he will talk about additive Gaussian noise channel. When I was an undergraduate student, I just could not understand why professors so much loved Gaussian noise channel. And that is because we handle radio communication mostly in communications course. In that case, thermal noise is unavoidable, especially with large, huge amplification in the receiver. And without other interference or RF nonlinearity or RF impairment, that is dominant. Got it? So when you see additive Gaussian noise, you may regard it simplest model. There are other much more complicated scenarios with interference, with nonlinearity in your transmit and receive amplifiers, something like that. Anyway, so channel basically introduces uncertainty. Now, before Shannon, people believed that if there is uncertainty, we can combat this uncertainty by carefully designing our encoder and decoder. However, for some channels, we may not completely remove our possible errors in recovering the message. So before Shannon, people believed it's impossible to completely remove error in communications if channel is bad. For example, channel is Gaussian noise. And interestingly, Shannon developed mathematical theory and says that as far as for the additive Gaussian noise channel with band-limited Gaussian noise channel, your additive Gaussian noise channel actually can still be used as a communication channel, error-free communication channel. And without error, still you may achieve a positive transmission rate, bits per second, as far as you have some non-zero power and some non-zero bandwidth. This is amazing result and shocked everybody. And it really contradicts our intuition. There is noise. How can we completely remove any possibility of making an error or making a statistical inference on the transmitted symbol? And interestingly, he used the theory of sequences. And one of the most unfortunate high school curriculum of Korea is that we do not seriously teach about the sequences in high school. And when I attended graduate school in the US, in my lab, there was an Indian student from one of the most prestigious Indian Institute of Technologies. And we had some discussions about our high school curriculum in two countries. And I was shocked because he said, I didn't verify, but he said that the mathematical analysis, 해석학, is taught in India in high school. So he just knew not only the convergent and non-convergent sequences, he also knew from high school what is, for example, the convergence of a sequence of functions. We are and we were taught some of them in our undergraduate studies. And even many of the so-called EECE students are not taught at all. Anyway, he double majored or minored mathematics, and he knew how to handle sequences using so-called limit operation. So actually, What he said about the probability of bit error is 0 or error-free. Actually, he didn't imply this. He said probability of bit error parameterized by some index can be arbitrarily small. And I once told you that whenever, as an engineer, you see this limit operation, you must interpret this as what? For sufficiently large n, you can make this approximation, right? So by designing a system, you make the error probability as small as you want. Maybe if your target is reduced, the system must be more complicated. However, still you can achieve that small one, right? So please remember this engineering equivalence. Whenever you see something like limit n tends to infinity of some sequence parameterized n equals 0, then you must interpret as for sufficiently large n, this approximation is well satisfied. Got it? So this seemingly equality formula actually involves some limit operation. Got it? So if you are really interested in taking the information theory course, for example, next semester, probably Professor Kim Yong-jun will teach this information theory in 500 level. And he's a very good teacher. But still, I recommend you study mathematical analysis a little bit more before you take the course. And that will give you your better understanding of information theory. Because information theory is all involves this constructing a sequence and showing the limit of the sequence equals 0 if it is, for example, bit error rate. And limit of the transmission rate can be as close as this number, something like that. So I strongly recommend you study mathematical analysis or 해석학 before you seriously study information theory. Of course, you can just manage yourself, but you will suffer a lot. But it will be really, really fun to combine this mathematical analysis and mathematical theory of communications via information theory. Now, let's see what kind of problems he tackled in his mathematical theory of communication. By the way, I remember that his PhD thesis was entitled as A Mathematical Theory of Communication. And after he became a professor at MIT, he co-authored with his colleagues a book. And the book has the title, The Mathematical Theory of Communication. So he was a little bit modest when he was a PhD student, and he became kind of very proud that his theory is the theory of mathematical communication. And this is the copy of the famous book, The Mathematical Theory of Communication. Let's see this one. So in this diagram, block diagram, there is one information source and one information sink or destination. So this is source and this is destination. And as you see, this is the channel. Got it? And there are many different types of channels. But in this figure, the additive, you see that this small block is actually the summation operation is performed. So noise is added to the signal that is generated by the transmitter or encoder. And here is the receiver. And here is the destination. So this is the encoder, what I told you. And this is the decoder, already told you. So again, you have what? You have three entities given already. Information source, information sink, and channel. And what you want to do is to design these two boxes. Now, as I told you, this channel introduces uncertainty, sometimes through deterministic mapping like squaring or taking the absolute value. Sometimes it adds noise, which is very well modeled as a random variable. Sometimes random process, sometimes random vector. Now, given this is one of the pictures, and this is about the information transmission. So this figure is related to one of the topics in information theory. How can we reliably transmit our message from the source to destination? How can we reliably? And if we involve this terminology reliably with our temporal concept, 시간 의미, then we have immediately realized that there are two performance metrics, error probability and transmission rate. Once I told you that I will transmit all the information of the world like this, and this sound level in dB, for example, contains all the information. Suppose we have converted all the information in the world to a binary vector. And we may just have this encoded into a decimal. Very large number, but will be finite. Now I put 0 and point and convert this pulse sound to this one, then I've transmitted everything, right? What is the problem? If you go down to a lower decimals, probably you may have more and more uncertainty. Your equipment may not measure that level clearly, right? So actually, even though I could reduce the transmission rate, but error rate increased. So initially, probability of bit error and transmission rate was thought to be a trade-off. And this trade-off is done something like that. You cannot reduce the probability of error without too much increasing the rate, right? So the reason around here is very hard to achieve. And here, this is easy to achieve. This is our common sense, right? So probably Shannon started from this idea. Okay, so what would be the mathematical theory that really solves the problem of communication? Probably he wanted to find out some theorem, lemma, or corollary that talks about this one. So given a channel, probably he wanted to know some Pareto optimal front ends, because now you have two performance metrics, and as you learned in introductory optimization theory. I heard that that introduction to optimization theory is one of the most popular undergraduate courses for our postdoc students. And at the end of some chapters, you have a multi-criterion optimization. I'm not sure whether you are taught about the concept or not, but if you haven't, I strongly recommend you also review that part by renting some books from our library or searching for YouTube lectures or some materials on the Wikipedia or something. Anyway, so this vague idea is mathematically theorized by Shannon, and amazingly, what he found is this one. We can make the probability of error arbitrarily small, so we can almost achieve 0. And this is possible up to some rate. So for example, he have found some curve like this. And interestingly, suppose this is bit error is 1/2 is the worst case, then it's equivalent to that he has found this curve using mathematics. And interesting thing is that here we can approach this point asymptotically, 점근적으로, okay? In some sense. So this is his idea, his result. And now, let's see another topic. Let me skip this one. Where is the compression? Yeah. Is there any better idea? Okay, let's take a look at this. And he also thought about how to convert the source output so that it can be better communicated through the communication device. So he focused on this problem, this sub-problem, like this. So source generates some information, but the source may generate some analog signal. And our up-to-date practice is to use analog to digital converter. But anyway, suppose you want to just convert this to a digital format. And your voice can be converted to an electrical signal using a microphone. But it's an analog form, in analog form. So what do we do? We usually use uniform sampler with finite quantization level. And if we just do the quantization, we have two problems. First one is that our sampling rate may introduce us some degradation in our conversion from analog signal to digital signal. For example, as you learned in signals and systems, suppose you have two different signals, M1 of t and M2 of t. But suppose you sample here and here, these 3 points, even though this is not uniform sampling, can you distinguish these two signals? Some information in between two consecutive sampling instants may be lost, right? Why this happens? Why this happens? This analog signal, say M, is what? As a mathematically speaking, is a function from R into R. Now, what is a function? It's a mapping from one of these set and one of this set. Now, how many elements do we have in the real set? Uncountably infinite numbers. Even though we restrict our time into a finite interval, for example, 0 to some 1 second, how many possible time instants do we have? Uncountably infinite. So analog signal involves uncountably infinite number of time instants. Now, we use a uniform sampler. We lose most of the informations in general, right? And suppose we use, as you see here, a uniform sampler. What happens? So if you have x of t, a continuous time signal, and you sample that every t s, and let's define this one as x over n, if you want, let's say that xd, discrete time, then in general, this uniform sampling gives us a lot of loss in the information contained in the message. And as you already, most of you already know, but under certain conditions, amazing thing happens. This possibly countably infinite. This has uncountable, it involves uncountable infinity, but here, this involves countable infinity, right? Countably infinite numbers can represent uncountably infinite numbers. That is the sampling theory. And under what condition? If the signal is strictly band limited. Just mathematically speaking, most of the simplest theorem says if our message signal is an energy signal and strictly band limited in terms of that the sum out of band power energy is 0, then what? Then under certain conditions, what condition? The sampling rate is higher than twice the maximum frequency content. Then our conversion from uncountably infinite domain to countably infinite domain lose no information, right? And that is Nyquist's sampling theorem. But actually, Nyquist developed the theory for deterministic finite energy signals. Shannon extended it in his information theory. So if you take the information theory course, you will see the term like Shannon-Nyquist sampling theory. Sampling theory. What's the difference of Shannon's sampling theorem from Nyquist's sampling theory? As I told you, Shannon was the person who could handle uncertainty mathematically. So this theorem actually starts from this. You have a random process. This is a random process, not a deterministic signal. Now it is strictly band limited. Then your uniform sampler, if its sampling rate is greater than or equal to twice the maximum frequency content of this random process, then allows you perfect reconstruction of your x of t. So x of t is perfectly reconstructed, can be. From what? From its uniform sample under certain conditions. The difficulty here is that also Nyquist's sampling theorem involves actually also the theory of mathematical analysis. Because we have a sequence of samples, right? given a function, if we take uniformly the samples from the continuous time signal, we have a sequence of real numbers or complex numbers, right? And the perfect reconstruction, this perfect reconstruction involves the idea of some limit operation. Again, it's like squared error or error tends to 0 under certain conditions. Got it? So you have infinite sum of something. And you may wonder, Nyquist sampling theorem involved some infinite summation? Yes. You remember that. In case without delta, you have some sync pulse, right? Something like this, right? And here, this summation is what? This summation is an infinite sum. And you know from signal-generation systems that actually this equality is not just a simple equality of two real numbers, right? Actually, this is what? Limit something tends to infinity. The limit is the same as this function evaluated as specific number. So actually, sampling theorem involves convergence of a sequence of functions. Actually, convergence of a series of functions. So now you understand how the mathematical analysis that teaches the theory of sequences of real numbers, real functions, complex numbers, complex functions is important in communication theory and also information theory. Anyway, so first what he did was that he extended Nyquist sampling theorem to involve random processes that had some uncertainties because he wanted to handle uncertainties. Second thing is this one. Now it is a common practice in our A to D converter that not only we sample the signal uniformly, but also we quantize the sampled signal using a finite number of bits. In general, some real number, a real number in general, cannot be represented by a finite number of binary symbols. For example, in our decimal number system, can you represent the number pi using finite number of decimal numbers? You can't, right? So if once we use finite number of bits to represent some number, we immediately lose information. So there are two things involved. One is the sampling itself. Another is quantization. And Shannon have shown something amazing. Under certain conditions, with finite number of bits, still you can perfectly recover the message. That is really, really amazing. And that is related with so-called vector quantization. But he also did some work on so-called lossy compression. So this involves uncountable infinity. So uncountable infinity is involved in an analog signal. Not only in this t-axis, but also in this m of t-axis, right? Because it's a real number. And the theory says that under certain conditions, we can represent this signal using a sequence of finite bits. But that may not be practical. So he divided this compression. So here you have a sequence of finite number of bits. And here is destination of a sink. You have m of t, some encoder. Here goes the decoder, M head of T. So there is no channel in this case. So you have source and sink, you have encoder and decoder, and here goes a sequence of finite number of bits. In this case, we may lose some information, but we may reduce the number of bits here. We do not want to lose any information. In that case, we may have some finite number of bits. So this is a problem of compression, and the problem of compression is divided into two compression problems. One is lossless compression, and the other is lossy or lossy compression. That allows some loss of information. So when we allow some loss of information, we know that we can reduce the number of bits to represent that one, right? So we can save instead of we lose some information. And he also tackled this problem very, very successfully. And actually, the idea of this lossless and lossy compression is used in our daily practice. For example, suppose you send an email to your friend, and you want to reduce the number of bits of your message. But still, you do not want to have any error introduced. In that case, when you compress and decompress, for example, you send a file that is very large and use RZIP, for example, you do not want to any information. In that case, your encoder, so-called source encoder, compresses the signal so that your source decoder can recover the message without any error. That is one problem. And the other is actually occurs here in our daily use of cellular phone, or your daily use of MP3 file hearing. Especially this MP3 compression method, it really uses our human beings' physiology. So it knows we have some audible range of frequency, and sometimes some information lost, but we cannot perceive. That kind of experiments done by the professionals in psychology, actually, 심리학과. So when we talk about some study in psychology, 심리학 study, we just think about how to understand the other person's intention. But actually, most of the study in psychology is all about how human perceives. So they study a lot about our vision system, auditory system, something like that. Skin sensation, something like that. And they have found and cooperated with electrical engineers and developed some idea how to systematically remove redundancy with very small loss. That is called psychoacoustic signal compression. Here, psycho means psychology. It's not psychopathic personality. Psycho means psychology. And so human-based signal compression method. And that's why some music, a lot compressed, but still we feel there is nothing lost. But for example, some extraterrestrial intelligence visiting Earth will find and say that, hey, your MP3 format is terrible. It loses too much information, it may say. Because this MP3 standard is highly fit to only our human being. Even your pet, cat or dog, may say that, our master just listens something broken music, something like that. Anyway, so this compression, data compression, so that we have no loss in information or very little loss in information to have finite number of bits or sequence of finite bits is also an important topic. And also, let me go up. The secure communication is also very important. It is not only important in compression. For example, when you use RGB or some other WinZips or something, you can encrypt so that some unintended receiver may not open the file or decompress the file, right? And in our communications, you want to make your message secure so that no eavesdropper can listen to your message, voice, something like that. So, and when the information theory was developed, it was just after the World War II, and everybody knows what is important in the wartime. Security, cryptography. So his information theory is naturally involved this encryption theory. And the problem is this one. If you go to the Department of Mathematics or Department of Computer Science and Engineering, and if you take a course on cryptography, they all talk about something totally different from information theoretic encryption. So this is called information theoretic security or encryption. And this is, unfortunately, is different from our daily practice to do encryption or to do improving security. Currently, most of our encryption method is based on some algebraic mathematics. So we want to have some very large prime number and another very large prime number. Sometimes it's hard to factor some large number, finding a prime number, and we use that idea. And actually, last night, Google announced their quantum computer and saying that they finished some computation in 5 minutes that ordinarily have taken more than the life of our cosmos, something like that. And I heard that the stock price of Google skyrocketed last night. Unfortunately, I don't have any stock of Google. But anyway, so the current practice based on this algebra may be very much challenged by a very fast computer. However, Shannon's idea is totally unrelated to that. Shannon developed mathematical theory. Even the most fast computer, some quantum computer, cannot break. So even though this is not the major stream in cryptography or communication security, information theoretic security and encryption, I believe, will get a spotlight in the near future. So if you have interest in it, I strongly recommend you take information theory. And even though your course may have much focus on data compression and data transmission, but your textbook will have chapters about information theoretic security. So based on what you learned through that course, you may self-study at least about the topic, and it may give you a very good career in the future. Nobody knows. Got it? And information theory is not only just simply represented by this communication channel with a single source and single destination. Now, the theory has evolved to much more complicated situations where we have more than one sources and more than one destinations. And sometimes the signals interfere in the channel with each other's signal, something like that. So there are many more channels complicated than this simple additive white Gaussian noise channel. And people have used their mathematical skill to derive some very unintuitive results. One amazing thing about this information theory is this. From the beginning, the results started to break down our so-called common sense. For example, noisy channel you have. You can never remove error in the destination. That is broken by information theory. Shannon showed that you can make the bit error rate arbitrarily small, but still keeping the transmission rate non-zero, some finite number. That is called the channel capacity, actually. You will learn about channel capacity, concept of capacity of a channel. And in many cases, this capacity is not zero, which means that you can transmit with arbitrarily small error at some positive rate. That is amazing. Before Shannon, people thought that in order to reduce the bit error, you have to slow down your transmission rate arbitrarily small. But Shannon showed that you don't need to do that. Okay? So it's like before, if you want to reduce the bit error rate, people thought that we have to reduce the transmission rate. But Shannon showed that we don't need to do that. Got it? Just a second. Is this figure correct? Yeah, I believe so. Yeah. Anyway. And you may see that the information theory is too mathematically abstract. That's why people have specialized the results so that we have modern communication system. So the story is like this. Let me show you the block diagram quickly. So in information theory, we start from this one, source, channel, and destination. And we want to design encoder and decoder. But for radio communications, channel is very special. And what do we have? It seems, yeah. We have modulator and demodulator so that our signal applied to the channel becomes a radio wave. And the output radio wave is converted to an electrical signal. So in radio communication, we must have these two blocks so that we can utilize the channel, wireless channel, by transmitting a radio wave. If we use different something for wireless communication, we may have different modulators and demodulators. So here we may say RF modulator that modulates the carrier. And here is something interesting. Before, we didn't separate source encoding and channel encoding. But under certain conditions, we can separate the encoder block into source encoder that only looks at how can we compress the source signal. So we compress the source signal as good as possible using source encoder. Interesting result is that if we remove all the redundancy, so we maximally compress some signal, then when the signal is represented by bits, the mathematical theory says that these bits look like IID bits with probability 0.5. So it looks like IID bits independent. So given the independent bit sequences, we design channel encoder that is best fit to our specific channel. This is called source channels coding, separate source channel coding. Separate. Shannon also proved that under certain conditions, you don't lose any optimality by just dividing the encoder into source encoder and channel encoder. And also, you separate your decoder into channel decoder and source decoder. However, you will see in the information theory that in some cases, this separation gives you suboptimality. Sometimes you have to design joint source and channel encoder. So this entire block must not only have the idea about what is the statistical model of your source signal, but also statistical model of your channel. That is one of the information theory results. And this is too much, I believe, but you will see some graph like this in your introductory digital communications. And here you have log scaled axis. And also you have log scaled axis. So such a log-log plot is very popular in digital communications and also in RF communications. You must be able to read the numbers. So this is one of my popular questions in signal gen systems. So suppose you have this number. What is it in the decimal number representation? What is this? Interestingly, many of you cannot read. So anybody? This is 2 times 10 to the negative 4. So this is 1 times 10 to the negative 4, and this is 2 times, 3 times 4, 5, 6, 7, 8, 9. So this is 10 times 10 to the negative 4, which is 1 times 10 to the negative 3. You must be able to read it as far as you are majored in electrical engineering. Anyway, you will see something interesting like this. So we are almost at the end of our information theory, and let's see some state-of-the-art information theory applied in our daily practice. So you use cell phone, and we sometimes transmit our voice message, sometimes we transmit our digital message. And the channel between our cell phone to the base station and base station to your counterpart may be a noisy channel or channel very prone to error. How can we reduce the error? We design so-called channel code. And channel code actually adds some redundant bits. And let me show you an example. Suppose you have 4 bits to transmit. Just a second. Parity. Yeah. But what you do is that you add 3 parity bits. So originally, you have 4 bits to transmit. After, for example, you compress your information bit. But now what you do is that you systematically add 3 bits so that when you receive 7 bits with some of the bits flipped, you can still recover the original data. The simplest one would be repeating the message, right? For example, 5 times. In that case, you add 4 more bits per bit, right? And probably what you do is that you can do some majority vote. But there are many clever ideas than that repetition. And this is another mathematical theory called channel coding theory. And channel coding theory is one of the most important things because your Wi-Fi, your cell phone has channel encoder and decoder so that it can systematically add redundancies so that even though you have noisy or interference-prone channel, you still recover or statistically best estimate your message signal. And that is actually covered in separate course. For example, if you look at the next semester's course list in our graduate program, you will see an error control coding course. Professor Yang Kyung-chul will teach. That is very mathematically heavy. It will talk about linear algebra on finite field. And many of you heard mathematician Galois, who developed some theory about finite fields. And finite fields is applied to design good codes, good channel code. So more than this simple idea. Anyway, our last pictures show some fathers of error control coding. And you see that he was a mathematician and did military service during World War II and seriously found the importance of error control. And he became a professor in electrical engineering and doing a lot of error control coding. And his name is also remains in some very famous encoding method and something like that. And this also shows some example. Suppose you have grayscale Mona Lisa, and you may have some bit errors so that you have noise. Without coding, you receive something. But with coding, possibly with some additional information that is not shown here, you can recover, for example, like this. That is the magic of error control coding. And this error control coding not only used in this image recovery, but also used in the old CD and DVD. Also, where it is? Oh, picture is gone. Also in deep space communication. In deep space communication, like Voyager, the spacecraft is far, far away. And even there is some cosmic ray, the received signal is just gone. But we want to recover the message from that spacecraft. What do? We put a very, very strong channel code, which means that we put a lot of redundancy systematically so that we do not too excessively encode, but we want to systematically remove the errors. So NASA, the 미 항공우주국, developed the error control code for deep space probes. And interestingly, this is what they've done. They put the strong encoder in the spacecraft, but they didn't have a decoder that works in very low SNR, but just launch it. And you know that it takes more than 3 or 7 years to reach some planet like Jupiter or Pluto. So they developed decoder that works perfectly at very low signal to noise ratio during the time when the probe reached the target. And amazingly, those images from the spacecraft is well recovered by the NASA engineers. And it was a great success of practical channel coding. Anyway, so I'm kind of wrapping up this course talking about some topics of information theory and error control coding, which are offered in the next semester. But for the target the target is the graduate student. So since many of you are undergraduate students, the course may be tough. But you may have interest and take the course, and nobody knows, you may find it the destiny of your career. By the way, we also offer the introductory undergraduate digital communications course. So I hope many of you take that. And I myself also teaches introduction to digital signal processing. So think about that. Okay, that's all for the course. See you in the final exam.